once we can identify how many significant figures are in a number, we can do calculations with those numbers. After we do our calculations, we will need to round. For the purposes of this class, we will be looking at whether the first number that gets dropped off is less than 5 or 5 or greater. If the first digit we are dropping is less than 5, we will round down. That means the last digit that we want to keep remains as is. For example, if we are rounding 7.94 to the 10th place, we are keeping the 7.9 and losing the 4. But before we lose the 4, it tells us whether to round up or down. In this case, since it is less than 5, we round down, and the 9 stays as is, giving us 7.9 for our answer. If the first digit we are dropping is 5 or more, we round up. That means the last digit that we want to keep will go up by 1. For example, if we round 7.95 to the 10th place, we are keeping the 7.9 and losing the 5. But before we lose the 5, it tells us whether to round up or down. In this case, since it is 5 or greater, we round up. The 9 gets rounded up to 10, so we keep the 0 from that in our 10th place and add a 1 to the 7, giving us 8.0 for our answer. There are two rules for calculations with significant figures, an addition and subtraction rule and a multiplication and division rule. The first step in any of our operations is to determine whether our numbers are exact or inexact. Exact values can be considered to have an infinite number of significant figures, so they do not affect the number of significant figures in our answer. For example, if I'm using the conversion 1 liter equals 1,000 milliliters, I can think of that 1,000 as 1,000.00000, etc. My second step when I'm doing an addition or subtraction problem is to figure out how many digits after the decimal each of my starting numbers has. My third step when I'm doing an addition or subtraction is to round my answer to the same number of digits after the decimal as whichever number has the fewest decimal places. For example, if I'm adding 9.572 and 82.76, I identify the first number as having 3 digits after the decimal, and the second number as having 2 digits after the decimal. Since 2 is less than 3, my answer will also have 2 digits after the decimal. Before I round, I do the full calculation with all of the digits and come out with 92.332. I identify which digits I am keeping and which digits will fall off. Since I need to round to 2 digits after the decimal, I am keeping the 92.33 and the 2 falls off. But before it falls off, it tells me whether to round up or down. Since it is less than 5, I round down. The 3 stays as is, and my final answer is 92.33. One thing that I have seen students do is to line up the numbers with the decimal points all in a column, like shown on the slide. Then you can draw a vertical dashed line after the number with the fewest digits after the decimal. In this case, it would go after the 82.76 and would end up cutting off the 2 in the top number and the 2 in the bottom number. This is a great way to remember to round based on digits after the decimal, but don't forget to look at that next digit that's being dropped off to tell whether to round up or down. What is 10.52 minus 8.955 using proper significant figures and rounding? Is it A, 1.57, B, 1.565, C, 1.6, or D, 1.56? I'm going to warn you right now that this is an all or nothing problem. You do not get partial credit for adding or subtracting correctly. I assume you know how to add and subtract. What I'm looking for is that you know how to apply the significant figures rules. So in this case, we're doing 10.52 minus 8.955. And we're using the subtraction rule, which is going to be based on digits after the decimal. Notice that all of the answer choices are actually variations on the same number. They're just rounded a little bit differently. So when I do the subtraction, I come out with 1.565, and I'm going to round it based on my significant figures rules. One of the things that I like to do for addition or subtraction is draw a little dotted line to remind me where to round. So since I've lined it up where the decimal points are on top of each other, I'm going to draw a dotted line right after my shortest number, the one that goes to the least digits after the decimal. So I'm going to cut off my number in between the 6 and the 5. But I can't just ignore that 5. That 5 is important. It tells me whether to round up or down. Notice I have 1.57 or 1.56 as an answer choice. So we're going to look at that 5, and because it's 5 or greater, we round up, which means we change the 6 to a 7, and the answer is 1.57, which is A. For multiplication and division, my first step is the same. Ignore exact values. My second step is different. Instead of looking for digits after the decimal, I'm looking for how many total significant figures are in each of my starting numbers. In step 3, I round my answer to the same number of significant figures as the starting number that has the fewest significant figures. For example, when I'm multiplying 4.38 by 695.1, first I do the math, and my calculator gives me something like 3044.538. I identify how many significant figures are in each of my starting numbers. The first one has 3, and the second one has 4. Since 3 is less than 4, I keep 3 significant figures in my final answer. This is going to be a little tricky because I have to round to a digit on the left side of my decimal point. Remember, we have to keep the same magnitude of our answer. So 3044.538, rounded to 3 significant figures, is not 304, but is actually 3040. However, if we write it as 3040, the significant figures are ambiguous. And if we write it with a decimal point after the 0, it conveys 4 significant figures when we can really only keep 3. Therefore, the only way we can write this number with proper significant figures is using scientific notation. Writing it as 3.04 times 10 to the third gives the correct magnitude of the number and the correct number of significant figures. What is 607.90 divided by 9,176.74 using proper significant figures and rounding? Is it A, 0.0662436, B, 0.0662, C, 0.066244, or D, 0.06624? This is a division problem, so we're going to use our multiplication and division rule, which goes by total significant figures. We are dividing 607.90 by 9,176.74, and we want to get proper significant figures out of it. Notice again that I've given you variations of the same number with just different rounding. So when we do this division, we'll come out with a number that has lots of digits in the calculator, and one of the ways that it could be rounded is 0.0662436, but we don't necessarily know if we're going to keep all of those digits. So we're going to count off the number of significant figures so we know how far to round it. Our top number has 5 significant figures. Remember, the 0 in the middle that's sandwiched is significant, and the 0 on the right is significant since there is a decimal point in the number. So all 5 of these digits are significant. Our other number has 6 significant figures. Since 5 is less than 6, we're going to round our answer to 5 significant figures. So when we round it to 5 significant figures, we can start counting our significant figures with our first significant digit. So we're not going to start counting 1 as the 0 here because this 0 is not significant, and neither is this 0. They are on the left side of our first non-zero digits, so they are not significant. It doesn't matter if it's to the left of the decimal or to the right of the decimal. We're talking about to the left of the first non-zero digit. So neither of these zeros is significant. Our first significant digit is this 6. So we're going to count 5 significant figures. So 1, 2, 3, 4, 5. Our fifth significant figure is this 3 towards the end of what I've written. So we're going to cut it off after that 3. But before we cut it off, we look at that next digit, the first one that's going to be dropped, and that tells us whether to round up or down. In this case, it's a 6, so we round up, which means we're going to be changing the 3 to a 4. So we're going to round our number to 0.066244, which has 5 significant figures. And that means that our correct answer is C. When we have multiple data points or types in our calculations, it is important to know how the level of precision of each of our data affects the level of precision of our overall answer. Here's an illustration of why this is important. In the 2016 Summer Olympics, as happens frequently, there was a 3-way tie for second place. You may be wondering, don't we have the technology by now to measure times more precisely than that? In fact, we can measure times very precisely, to the millionth of a second. However, when finding the fastest swimmer, what we really want to know is speed. The calculation for speed involves both time and distance. Although we can measure time very precisely, the way that the swimming pools are manufactured means that we are less sure about distance. There is a tolerance of about 3 centimeters in each lane. The low precision of the distance measurement leads to a low precision in calculating speed, so it is not possible to tell who really was the fastest. It could be the one who took slightly less time, also has slightly shorter lane. In the lab, we also need to be careful to do our calculations with the proper significant figure rules so that we can find the true precision of our results.